The concept of the electromotive force can be confusing, but it's a central concept in understanding Faraday's law, so I want to discuss it a little bit in detail here. First off, if you've got some device, some mystery device, and if you connect a circuit up to this device, a closed circuit, so we have a resistor, let's say, connected to the device, and if the device is supplying electrical energy and current is flowing through the resistor, then this device is a source of EMF. A source of EMF. Devices that can provide EMF include electrochemical cells, think of batteries, thermoelectric devices, solar cells, photodiodes, electrical generators, transformers, even Van de Graaff generators, etc. Now, the first point of confusion for EMF is the units. So the units of EMF are joules per coulomb, which is equal to volts. So even though EMF stands for electromotive force, the units of EMF are in volts. So one way to try to reconcile this is to say, well, joules is work, right? And work involves force. In fact, 1 joule is 1 Newton meter. And so while the electromotive force itself is not a true force, it's not defined as a force, it still involves the forces that are responsible for driving a current around a circuit. So let's try to develop a definition, a mathematical definition for the EMF. To do this, let's define a closed path C, which is simply a loop in space. So here's our closed path C. We can call this closed path C a circuit, in quotes, though it may or may not be part of an actual circuit with material objects such as wires, resistors, capacitors, batteries, and all that stuff. So it's just a general path in space where electromagnetic fields exist. Now what we want to do is circuit this circuit. So what I mean is we want to start at a point and mathematically, abstractly, walk around our closed path C and end up at the point that we started at. So what we need to do is define a positive direction of traversing the loop C. So let's define our positive direction going this way. Maybe we'll put a little plus sign here. Now, we're not just going to walk around this circuit willy-nilly here. We want to do something. So we're going to carry a positive test charge Q with us. So I'll put a little plus and give it the name Q. And as we move our positive test charge around this loop, we notice that there's going to be forces exerted on this test charge. These forces come from the electromagnetic field itself, as well as possibly by additional energy sources such as batteries that can interact electrically with Q. So we've got forces, and the net force on our positive test charge at any position we'll call F for force. And we start out and we notice something. We notice that the force F is proportional to the charge itself. So let's define little f. Little f is the force per charge, sometimes called the force per unit charge. So little f is independent of the actual quantity of charge that we're carrying around this circuit. And it's independent of that because the force is proportional to the charge itself. So if we take the force and divide it by the charge, we get a number, which is the force per charge, that is independent of the charge itself, which we're calling little f. So as we move our positive test charge Q around the closed path C, in general, there's force exerted on Q at every step of the way. And EMF is the work done by the external force F per charge as we move once around our closed loop C. And here's the mathematical equation for the EMF that actually computes what I just said. So the EMF of our circuit C at some time t is the line integral of little f, which is the force per charge, along our path C, taken in the positive sense of C, so taken in the direction that we defined to be positive. And notice that the EMF is independent of the particular value of our test charge Q. And it's also worth mentioning that we are assuming that our test charge Q is small enough such that it's not perturbing the position of external charges. Maybe there's some charges out here, positive and negative. This test charge Q is not perturbing the positions of these external charges, so it's not perturbing the electromagnetic field itself that's producing this force F. Okay, let's talk about EMF and batteries. So if you've got a 9-volt battery, shiny new 9-volt battery, we have our cathode and our anode. What this is this is a device that supplies a voltage equal to 9 volts. So people say the voltage of this device is equal to 9 volts. And a completely equivalent way of saying this is that the EMF is equal to 9 volts. This device supplies an electromotive force equal to 9 volts. So people will use the word voltage and EMF interchangeably. And if you took this battery and you connected it to a voltmeter, so an ideal voltmeter such that it has an infinite impedance, therefore it draws no current from your battery, the voltmeter would read 9 volts. A voltmeter measures the potential difference. Potential difference, so another term, across the terminals of the generator. So the potential difference would even be 9 volts. Again, assuming that the current is equal to 0, so this voltmeter is ideal. Now I'm going to prove this, but we need first a good definition of the potential difference. So let's suppose we're in a region of space, and in this region of space there happens to be an electric field, E. The electric field can be written as a sum of two components. One component is conservative, so E sub, we'll just write it all out, conservative plus E non-conservative. A conservative field has the property that if you take a closed line integral around a contour C, you get 0. A non-conservative field does not have this property. So if we took a closed line integral around path C of a non-conservative field, in general, this is not equal to 0. Conservative fields are produced by charge concentrations. Non-conservative fields are, I don't want to say the word produced. Some people would say they're not produced by changing magnetic fields, but they're at least associated with changing magnetic fields. When I say changing, I mean time varying. So maybe let's put that in parentheses. Time varying magnetic fields. And that's it. These are the two things that produce electric fields. Charges and magnetic fields changing in time. Now, when people talk about the potential difference, and they use that term, they're usually assuming electrostatic potential difference. What that means is you're in this region of space, and within this region of space, the magnetic field is static. It's not changing with time. And therefore, the electric field is conservative within this region of space. And we know that the E field is produced by concentrations of charges. So we'll just write charges. That's what's producing the electric field in this region. And now we're in a position to define the potential difference. The potential difference is the net work per unit charge that you have to do against the electric field to move a positive test charge from point P1 to point P2 along a path C that exists within this region of space in which the magnetic field is not varying in time. Mathematically, I can express the potential difference between point P sub 2 and P sub 1 as V sub 2, 1, which is equal to the potential at point P sub 2 minus the potential at point P sub 1, and this is equal to minus the line integral of E dot dl from point P1 to point P2 along our path C. And because our electric field is conservative within this region of space, it doesn't matter what path we take. We can take a crazy loop-de-loop path. Let's call this path D. If you perform this line integral, it's going to be the same thing as if you went just on path C. And so the potential difference between point P2 and point P1 does not depend on your path, so long as your path is through a continuous region in which the magnetic field does not vary with time. Now, there are many names for the potential difference. Here's one: difference of potential, difference in potential, or sometimes difference in electric potential, voltage difference, just simply voltage, electric field potential difference, electrostatic potential difference. Oh, and I just thought of another one. They also call it the voltage between points, in this case points P sub 2 and P sub 1. The key thing to remember is that the voltage between these 2 points, or the potential difference, or whatever you want to call it, is unique. It's unique so long as you're within a region of space in which the electric field is completely conservative. Now, if we were in a more general time-varying situation in which the electric field is not conservative and the magnetic field is dynamic, so its time derivative is not equal to 0, you can still define a potential difference between point P2 and P1. And there's a few actual definitions that I've seen, but the one that I think is probably correct is that V sub 2, 1 is equal to negative integral. We're going to take a line integral from point P1 to point P2, and you're only going to take the line integral using the conservative part of the electric field. And you can do this, but this number that you get for the potential difference is kind of meaningless because you have this non-conservative component of the electric field. And so the number you get for V sub 2, 1 when the electric field is not conservative does not actually tell you the work required to move a positive point charge against the field from point P1 to point P2. So you can define it all you want, but it's not as useful in a time-varying situation. So let's suppose we have a battery, which is some strange shape. This is our battery. And due to electrochemical interactions, the battery is going to be producing a force that's exerted on electrical charges. And this force may be uniform throughout the battery or may not. Let's say it's pointing up. So F sub bat, and in general, it's a function of x, y, z coordinates. It's important to remember that this force, F sub bat, exists only in the battery. Outside the battery, the force is 0, and in general, this force, sub bat, is non-conservative. It's a non-conservative force. So let's draw some terminals on our battery. And we know that this battery is not connected to anything. So the current in this battery must be 0. Has to be. But we have a force that's exerted on electrical charges. Force pushes charges, yet the current is 0. So what's going on? What happens is essentially a feedback process. Force, F sub bat, pushes on the charges, separates the charges, and you're going to get a charge separation in which the positive charges are pushed to the surface of the battery in the top half, and negative charges pushed to the bottom half of the battery. So the battery produces a charge separation. So this charge separation is going to produce an electric field of its own. Let's move this here. Electric field will be, something like this. Will be down, something like that. Now, if you look, we have two regions of charge, a positive charge and a negative charge. So outside the battery, the further you get away from it, the more and more it looks like an ideal electric dipole. So I'm kind of drawing some electric field lines here. And it's important to remember that outside the battery, there is no time-varying magnetic field, and the electric field is completely conservative. So you can write the electric field is conservative. Good to remember. The electric field outside the battery is due only to the charge separation, and the charge separation is due to the internal force F sub bat. And it's important to remember that this F sub bat is probably extremely complicated. There's ions involved, there's all sorts of stuff involved, but we're abstracting all of that away into just some general non-conservative force called F sub bat. Okay, so inside the battery, the electrostatic E fields produced by this charge separation is going to perfectly cancel out F bat. I'm tired of saying F sub bat, so F bat, force due to the battery. It has to be, right? If there was a force inside the bulk of the battery, then a charge would be moving, and the charge would then accumulate at one end of the battery, and then that charge would contribute to the electric field that would slow down the next charge that's there. This is a feedback process. And we have this equilibrium that is achieved inside the battery. So inside the battery, let's just write this out. We have F bat, which again is a function of x, y, z. This must be equal to minus the electric field, which is also a function of x, y, z, due to the charge separation. And this equivalency holds for every point, every position in the battery. All right, let's calculate the EMF. Now we're going to need a path, so I'm going to use blue. So our path is going to go straight through the battery and out the cathode and then back into the anode. So here's our path C for calculating EMF. And we recall that EMF is equal to line integral f dot dl around our closed path C. And our positive reference direction for path C is shown by this arrow. So it's useful to label the anode and cathodes of this battery. Let's label the anode A and the cathode B. And we note that there are two distinct segments of our path when we're computing this line integral for the EMF. One segment goes from A to B through the bulk of the battery, and the other segment goes from B to A outside the battery. So with that said, we can write the equation for EMF as a line integral of F dot dl from A to B, and this is inside battery, plus, erase that arrow, plus a line integral of F dot dl from B to A outside the battery. And we remember that little f, this is a vector, is the force per charge. Now outside the battery, this guy is equal to our electric field. Inside the battery, there is no force per charge because the electrostatic fields produced by the charge separation perfectly cancels out F bat, and so this integral is 0 because F is 0 inside the battery. So now we're left with EMF is equal to the integral from B to A, E dot dl, and this line integral is taken, outside the battery. And we recognize this as the potential difference V sub BA, which can also be written as the electric potential at point B minus the electric potential at point A. This is the voltage across the terminals of the battery. So let's sum up what we just found. If you have a battery and you want to know what is the EMF that this battery generates, what you do is you connect this battery to a voltmeter that draws negligible current, and you measure the electrostatic potential difference between the positive and negative terminals of the battery, and that is the EMF. So we'll call this VBAT, and VBAT is equal to the EMF of the battery. This brings us to the topic of EMF and Ohm's law. Here we have a battery with a resistor connected across its terminals. The dimensions of the battery are L1, that's the length of the battery, and A1 is the cross-sectional area, and the battery has a conductivity of sigma sub 1. The resistor has a length of L sub 2 and cross-sectional area of A sub 2 and a conductivity, an electrical conductivity of sigma sub 2. Now let's compute the EMF in a closed path C that runs parallel to the wires in the circuit. So now our closed path C is actually a circuit itself. And the direction that we're going to walk through this closed path C is going to be in the same direction that we know that the current is flowing. So in this direction. Now the general form of Ohm's law states that J is equal to sigma times F. J is the current density, and its units are amps per meter squared. Sigma is the conductivity in Siemens per meter. And lowercase f, this is a vector, it's the force per charge. So this is newtons over charge, so coulombs. And it's worth noting that most people know Ohm's law as J is equal to sigma times the electric field. And this is a special case of the more general Ohm's law. So what we want to do is combine Ohm's law with our definition for the EMF. And when we do that, we get the EMF is equal to 1 over sigma times the line integral of the current density around our closed path C. So let's zoom out a bit and make some simplifying assumptions. The first assumption will be that the current flowing through the resistor, I, is equal to the current flowing through the battery. If this was not the case, then there'd be charge buildup. Like, for example, if there's more current flowing into the resistor than through the battery, then positive charge would be building up at one end of the resistor and negative charge would be building up at the other, and we would not be talking about a condition of equilibrium. We would not be talking about a DC circuit, but this is a DC circuit. The other simplifying assumption is to realize that the current density is uniform throughout the resistor and the battery. So, with these assumptions, let's write an equation for the magnitude of the current density in the resistor. This guy is simply equal to the current that's flowing through the circuit divided by the cross-sectional area of the resistor. And the current density in the battery is equal to the current flowing through the battery, I, divided by the cross-sectional area of the battery. We also note that if we took a line integral J dot dl and we're inside, let's say, the resistor, and we're going from one end to the other, so let's label this end 1 and end 2. So we're going from 1 to 2 inside the resistor. This would simply equal to J, the current density inside the resistor, times the length of the resistor. And that's because J dot dl are in the same direction. So J dot dl, the vector J dot the vector dl is equal to just the magnitude of J times the magnitude of dl. And then because J is uniform throughout the resistor, because we're not assuming that the cross-sectional area changes, when you take this line integral of J dl, it just becomes J times the total length. And then we can rewrite this as I over A, the cross-sectional area of the resistor, times the length of the resistor. Now, how did we get that? That was from this equation up here. Substituted it. So with these simplifying assumptions, we can rewrite our equation for the EMF as I times the length of the battery divided by sigma battery, that's the conductivity of the battery, times A, the cross-sectional area of the battery, plus I times the length of the resistor divided by the conductivity of the resistor times the cross-sectional area of the resistor. And we recognize this as the resistance of the battery. And we recognize this as the resistance of the resistor. So now we have an equation. EMF, the electromotive force, is equal to I times the resistance of the battery plus the resistance of the resistor itself. And from our earlier discussion, we also know that the EMF is equal to the potential difference between the terminals of our battery when the battery is open circuited. So we can write this as equal to VBAT, and we'll put a little maybe superscript OC to remember that we're talking about the open circuited voltage across the battery. And so we want to model this with a circuit, right? So this situation is simply equal to an ideal voltage source, which is the source of our EMF, which we know is the battery voltage when the battery is open circuited. And then this is going to be in series with the internal resistance of the battery. And then this is in series with the resistance of the resistor itself. So now let's talk about EMF and Faraday's law. To do this, we need to draw a closed path C. Now let's make it a little nicer. Let's go simple too. Here's our closed path C, and we need to define a positive direction, so that's what I did with this little arrow as we walk around this closed path. And now let's consider an open surface S that's bound by path C. So it looks like a little hat, for example, a little cap that we have. And so this guy is surface S. And we need to define a positive reference direction for our surface S. Now, that's actually already defined with the right-hand rule. So what I mean is, take your right hand and curl your fingers in the direction of our path C, so in this direction, and give the circuit a thumbs up, and this is going to define our positive reference direction for path S, which is pointing up. I'll just put N hat. Faraday's law states that the electromotive force around path C is equal to -1 times time derivative of the magnetic flux flowing in the direction of N hat in this figure, in a positive direction according to the right-hand rule. The magnetic flux flowing through our surface S, we can write as this integral. Surface integral, we're integrating over our surface S of B dot ds, and let me draw ds here. Here's a little patch of surface with area ds, and our vector ds is pointing out, and our positive reference direction as defined by the right-hand rule. So one thing I want to say about all this is, let's suppose you've got a coil of wire, and each loop in the coil has the same cross-sectional area, like this, and there's N loops. So N loops in this coil. And let's suppose that the magnetic field is applied from some external force and it's going right through this area. And the magnetic field in general is changing with time. And we're going to assume that we can ignore the magnetic field outside the region of the loop. So just outside the region, the magnetic field is basically 0. So what's happening is we've got some magnetic field changing in time, and each of these loops is going to be generating an EMF. So it's almost like if you expand the loops, it's hard to draw actually, kind of like this. Each loop is going to be generating EMF, and the EMF is equal to -1 times the time derivative of the magnetic flux. So the total EMF that's being generated here by N loops is equal to N times negative time derivative of the magnetic flux. And this is assuming that the magnetic flux, the same magnetic flux, is flowing through each loop, and it's the same. So we're assuming that there's no variation in the magnetic flux through any given loop in this system. Now what this EMF is going to do is push positive charges to one end of this open circuited loop system and negative charges to the other. And these guys are going to produce an electrostatic field. We'll just call this V term for the voltage across the terminals. And because we're dealing with an open circuited source, the electrostatic potential that you would measure with an ideal voltmeter is equal to the EMF of this source. So EMF is EMF. It doesn't matter, in a sense, what's producing the EMF. The definition is still the same. And the effect is still the same. If you connect this transformer, I mean, that's what this is, it's a transformer, and you connect it to an external resistor, R, the EMF is going to produce a current that's flowing through the resistance, or the resistor. And you can model this whole thing using circuit theory as a source of EMF, which is numerically equal to, again, the open circuited, let me put it OC for open circuited, the open circuited electrostatic potential that you would measure with a voltmeter. Then there's going to be, of course, some internal resistance in these wires, right? These are not in general ideal wires, so they have some resistance, some conductivity to them. And then this thing is connected to your external resistor, R. And then you can calculate the current that's flowing using Ohm's law.